All right, so we've got a couple people asking me about polynomials and about how you deal with complex roots. And so I just wanted to go through an example where we have a polynomial like this, and we are told that the number 2i is a root. So one thing that's immediate for me is that if we know one complex number is a root, then we know that its conjugate is a root also. And the way that we know this is when you multiply a complex number by its conjugate, they always cancel out to give you a real number. And the polynomial is what you get after you multiply out the factored form. So here's the idea. We know that this is going to have 4 different roots. We know that one of those roots is 2i. So I know that one other of those roots needs to cancel out 2i to give me my original polynomial. And the only number that cancels out 2i when you multiply it is the conjugate, is positive 2i. We need it to cancel out exactly, and anytime you do a complex number times its conjugate, so a plus bi times a minus bi, if you FOIL that out, you get a squared plus abi minus abi minus b squared I squared. The imaginary parts cancel out, and I squared is -1, so you end up with a squared plus b squared. So anytime your original polynomial has real numbers, real coefficients, then any root that is complex must also have a conjugate pair to match up to cancel out all the imaginary parts. Okay? So we'll come back to this in just a second. But for right now, I'm going to save this. I'm going to use the fact that 2i is a root, and I'm going to plug it in. If something is a root, that means if you plug it in, you end up with an answer of 0. So let's plug it in. And let's set it equal to 0. 2 to the 4th is 16. Negative 2 to the 3rd is 8. So I have 8i cubed. Here I have 4 times I squared. Sorry, I missed my I to the 4th. Here I have 2ai. Here I have 24. All right, so now I just go through. I to the 4th is positive 1. I to the 3rd is -i, so I have plus 8i. I squared is -1, so I have -4. Plus 2ai minus 24 equals 0. The real parts go away, and then the imaginary parts also need to equal 0. So I know that 8 plus 2a is equal to 0, which means a is equal to -4. You know, as I'm looking at this, I pulled this example out of the textbook, and I'm realizing something is wrong because, okay, I made a small mistake. Here I have 2 times 2i squared. 2 squared is 4 times another 2 is 8. So that would make this into -8. But I'm noticing that there's another mistake. And the other mistake is that the real parts don't equal 0. So the textbook messed up. Because if you look at the real parts, 16 minus 8 minus 24 is not 0. So let's fix that. Let's change the problem here. If we make this into a -2, make this into a -2, that switches this to be -8i squared, switches this to be plus 8. Okay, so now it really does actually equal 0. So the textbook screwed up, but we were still able to figure out that a has to be -4 to at least make the imaginary parts go away. Okay, so now we know a equals -4, and we know 2i is a root, and we know -2i is a root. So here's the next part of the problem. Remember, we're changing our problem to actually work. We found that a was -4. And And we know that this is going to factor to be x minus 1 root, x minus another root, x minus 2i, and x minus negative 2i. So that comes, if you multiply that out, you get x squared, negative 2ix, positive 2ix cancels. Negative 2i times positive 2i becomes 4. So we know that something times x squared plus 4 equals the original polynomial. So we can do polynomial long division with x squared plus 0x plus 4 on the side. And then in here, we're going to fill in the different terms. So the only way to get x to the fourth is to do x squared times x squared. X squared times 0x is 0x cubed. X squared times 4 is 4x squared. And then I look at the original polynomial. The original polynomial has negative x cubed. So I need to go negative x cubed here, which means we have negative 1x. That makes 0x squared. That makes negative 4x. Now let's look at our x squareds. We have negative 2x squared. I already have in the bottom left corner 4x squared. 4 minus 6 is negative 2. So this needs to be negative 6x squared. X squared times negative 6. This is 0x again. You really don't need that middle row, but I just wanted to show each and every piece. And negative 6 times 4 is negative 24. So now we have all the pieces that we wanted. So what we know is that our original polynomial now can be factored to be x squared plus 4 times x squared minus 1x minus 6. X squared plus 4, remember, is the x plus 2i times x minus 2i. And the other part is x minus 3 times x plus 2, which gives us the 4 roots of plus or minus 2i, that's 2 of them, 3, and negative 2. So what threw me off there was that first part was wrong. So they somehow messed up in writing the textbook, and they had a positive 2x there, positive 2x squared, which doesn't work out. So anyway, to summarize, your big idea is that if you have a root that's complex, you know the conjugate's also a root. If you plug in a root, you get an answer of 0. If you take your two roots and multiply them, you can do polynomial division, where you take your original polynomial and divide by the quadratic that you get from your complex roots, and then you'll be left over with a smaller polynomial that you can usually factor. All right, let me know if you got any other questions.